So this is what we studied in the last class, stoichiometric defects under the Schottky and the Frankel, and what are the conditions and what are the consequences of those defects. And next one is the non-ionic compounds and what are the defects possibility in the non-ionic compounds and like covalent compounds. Vacancy and the interstitial defect. Vacancy defect is similar to the Schottky defect. That means the atom will be missing from the lattice point so that the density of the solid will decrease. Okay, so it is shown only in the covalent compounds. Interstitial defect is what? It is same as the Frankel defect in the ionic compounds. The atoms will go and occupy the interstitial site in the given lattice. What is the meaning of interstitial site? It is an empty space between the two solids in the given solid. Sorry, it is an empty space between the two spheres in the given solid, that is called as an interstitial site. So if the atom is going and occupying the interstitial site, that is a interstitial defect. Fine. Any doubts up to this? So now we are going to discuss about the non-stoichiometric defect today. The first one. So in the case of non-stoichiometric defect also, we have the two types. One is a metal excess defect and next one is a metal deficiency defect. Next one is a metal deficient defect. So what is the meaning of metal excess defect? What is the meaning of metal excess? Listen here. I'll explain the diagram. Suppose you have taken the sodium crystal here. Like this. Okay, you have taken the sodium crystal. Sodium chloride crystal, sorry. You have taken the sodium chloride crystal. In that we have the positive charge and the negative charge. Okay, negative will take it to orange color. So this is a sodium chloride crystal. In that we have the both positive and the negative. Negative is nothing but the Cl and the positive is the Na atoms. Now above this crystal, what we'll do now, we'll take the only the sodium part. So along this crystal part, this region is there, right? So this region will take only the sodium part. So when you're heating this NaCl crystal in the presence of sodium, now we are heating the NaCl crystal in the presence of sodium. What will happen when you are heating the sodium? It will split up into the Na plus 1 electron. Yes or no? When you are heating the NaCl crystal in the surface or in the presence of sodium, the surface sodium will split up into the Na plus 1 ion and the 1 electron. Okay, now if it want to form the NaCl crystal on the surface, suppose on the surface you want to form the NaCl crystal, what we need, if you want to form the NaCl crystal on the surface of the given solid, what is required here again? Only Na plus 1 ion is there. Okay, but Cl minus ions are missing, right? Are you understanding what I am telling? So from where the Cl will get? If you want to form the NaCl on the surface of the crystal, we have already Na plus ions, but Cl minus ions are missing. So that what will happen, right? whatever the Cls are there inside the crystal, it will goes to the surface. Okay, so whatever the Cls are there inside the crystal, it will goes to the surface and will form the NaCl. It will go to the surface Cl minus. So this Na plus and Cl minus will combine to form NaCl. But whenever this Cl minus is missing this lattice point, there is a creation of empty space around this one, right? Yes or no? Now the empty space is there in the crystal. This empty space is filled with the help of this electron. So whatever the electron is there, it will go and occupies this empty space. So this center is called as an Farben center. Epicenter or the Farben center, which cause the color to the crystal. Understanding now what is the metal excess defect? Listen here carefully. We have taken the first, the sodium chloride crystal, NaCl solid. In that both Na plus ions will be there and the Cl minus ions will be there. Now we are heating that NaCl crystal in the presence of sodium vapors. So when you are heating this in the presence of sodium vapor, the sodium vapor will ionize and will form Na plus 1 ion and the Cl minus 1 ion. Sorry, Na plus 1 ion and the electron will form. Okay, now if it want the NaCl formation on the surface of the crystal, the absence of chlorine will be there. So these chlorine will get from the inside the crystal itself. So whatever the chlorine atom are there present inside the crystal will go to the surface. Now it will go and combine with the Na plus 1, so it will form the NaCl. Now wherever the Cl atom is missing inside the crystal, it is an empty space. So to maintain the electrical neutrality, that means how many positive charge are there, same number of negative charge to maintain, this electron will go and occupy the crystal lattice point of the anionic site. So whenever the electron is occupying the anionic site of the crystal lattice, it is called as an Farben center or the F center. Okay, is it clear now? Is it clear or not?
Yes, sir.
Yes, sir.
So what is the meaning of F center?
To maintain electron neutrality, electron is added in the place of Cl minus.
F center is nothing but the anionic site of the crystal, the anionic site of the lattice point, which is occupied by the electron. Okay, that is called as an F center. Whichever the anionic site is there, it is occupied by the electron inside the crystal. That is called as an F center. The main cause for the F center is which will cause the color to the crystal. Okay. So if you take the NaCl, it will cause the yellow color to the crystal. Understanding? Because whenever this electron is coming and occupying this interstitial site, it will absorb the energy from the visible spectrum. So after the occupying the site, it will release the energy also in the form of visible spectrum. So which will cause the color. Clear now? Now tell me, when compared to the positive charge, negative charge is, sorry, when compared to the Na plus ions, Cl plus ions is more or less in the crystal. When you are comparing the Na plus ions and Cl minus ions, which ions are more now inside the crystal? Fast. You can see plus charge are the Na plus, right? Minus charge are the Cl minus. But when Cl minus went to the surface, that means Na plus ions will be greater than Cl minus ions, right? So if the Na plus ions are greater than Cl minus ion means there will be metal excess in the given solid or not? Can you see what I have written here? Or it's very light? If you take the given solid, the number of positive ions are more, the number of Na plus ions are more, because the Cl minus ions are going to the surface and combining with the sodium vapor. But the sodium ions are not going to surface, right? So metal ions will be more than the chlorines. So this is called as metal excess defect. Clear? So if you take the NaCl crystal itself, the color are very important for the board point of view and for the exam point of view. So if you take the NaCl crystal, due to the Farman center, it will cause the yellow color. Okay, and if you take the LiCl crystal, it will cause the pink color. And if you take the KCl crystal, it will cause the violet color. So these are the three crystals when you are heating in their respective vapors, which will get different colors. NaCl crystal will impart the yellow color, LiCl will impart the pink color, KCl will impart the violet color. This is all about the metal excess defect. And one more defect is also possible. Is there metal excess now? This is the first one. The second one is when you are heating the zinc oxide. I'll write here itself. When you are heating the zinc oxide, it will form Zn plus 2 plus half of O2 plus 2 electrons. So these 2 electrons will also impart the color. Initially, if you take the zinc oxide, which is white in color, but when you are heating this crystal, it will change into the yellow color because of these 2 electrons. Okay, so this is also called the metal excess defect, which will consider the metal excess defect. Now we'll come back to the topic metal deficiency defect. If you have any doubts in this metal excess, you ask me. Otherwise, we'll go to the metal deficiency. What about the metal deficiency? Here metal atoms are more, so only it is called metal excess. Metal deficiency means what? Metal content will be less. Okay. Suppose you have taken one crystal like this. Okay. And in this you have taken the A plus. Wait, I'll draw the neat diagram. Suppose you take A plus charge and this also plus A plus like this. And these are the B minus. Now, suppose if you take the example like FeO. Fe will show two oxidation states, right? It can show either +2 charge or +3 charge. Okay, Fe will show two oxidation state, either +2 or the -2. Suppose if you take FeO, Fe has both the chances. It can show either +2 or +3. Now, suppose if one of the cation, like if you take this cation, if this cation is occupied by the, instead of A plus, it is occupied by the A+2 ion, whether charge balance will happen? Whether charge balance will happen or not? No, right? Because one plus charge is extra is there. Instead of A plus, it is taking A+2. That means another A plus you have to remove. So when you are removing this A plus, now what is causing here? The metal atom deficiency is causing, right? Are you understanding what I'm saying? If you have the all A plus, A plus, A plus, or B minus, B minus, B minus is there, not fine, because you have total 3 pluses, 3 minuses. But when you are forming the compound, which are showing the variable valences, in one of the case A plus 2 is forming now, the charge will not balance, right? Now it becomes +4. A plus 1 plus 2 plus 1. So it becomes +4. To maintain this charge balance, we have to remove one atom. Okay, so we remove this one. Now this one will be cancelled. So it will maintain the A+3 and -3. So to remove this atom is nothing but causing the metal deficiency in the solid or not. That is what the metal deficiency defect. Understanding? So metal deficiency defect is possible in the compounds in which metal atom will show variable oxidation states. Variable oxidation state is nothing but the same metal atom will show +2 charge or the two different oxidation states.
Let's break out and
Just wait a minute. Can you see the screen now?
yes, sir.
Okay. Is it clear? Whichever the metal atom is showing the multiple oxidation state, which will cause the metal deficiency defect. Clear? So this is all about the non-stoichiometric defects. So next we'll go to the one last thing is impurity defect. Okay, if you finish the impurity defect now, everything will be finished. The defect in the solids. So impurity defect, it is also called as an extrinsic defect. Okay. So suppose you have taken the NaCl crystal, which are doping with the CsRCl2. Okay, just take the NaCl crystal. In the case of NaCl crystal, what is the Na plus charge? +1, right? And Cl minus 1 charge is -1. What about SrCl2? Sr will show +2, Cl will show -1. So this is a doping process. What is the meaning of doping? Anyone? What is the meaning of doping? Adding of impurities to the given solid. That is called as doping. Okay, to increase the electrical conductivity, we'll add some impurities to the given solid. That is called as doping process. That we'll study after this defects topic. What is the complete doping and all. Now, suppose you are taking the crystal like this. But sir is always drawing the circles and all. Are you understanding why I'm drawing all these things? Is it clear or not?
Yes.
+1 means what? Na atom, and -1 means what? Cl minus atoms. Now you take, these are NaCl crystal we have taken here. Now this NaCl crystal is doping with the SrCl2. Okay, so Na will show only +1 charge, Sr will show +2 charge. Now when you are doping with the higher valency elements, Na is a +1 charge, right? So when you are doping with the higher valency element, what will happen? This Sr will go and occupy the 2 Na plus atoms. Each Sr will go and occupy 2 Na plus atoms. Why? What is the main reason? What is the main reason here? We are doping with the SrCl2, right? So each SrCl2 will be equal to the 2 Na plus ions, because Na will show +1 charge and Sr will show +2 charge. So maintain the electrical neutrality. Okay, to maintain this electrical neutrality, each Sr +2 ions will occupy the 2 Na plus ions, such that Sr will go and occupy only one side of Na plus. It will cause other of the side will be the vacant space. Yes or no? Are you understanding what I'm telling? Or can I explain once again?
Mm.
Preeti, Dhairya, Ramcharan, Vishwanath. Sorry.
Okay, sir. Continue.
What is the main thing here? Whenever the higher valency elements is doped with the lower valency element, the higher one will occupy the either double or the triple based upon the lower valencies. Like if you take example like NaCl and SrCl2, each Sr plus 2 ions will occupy the 2 Na plus ions in the crystal lattice. So that Sr plus 2 ion will go and occupies only one side of the Na plus ion and will keep the remaining Na plus site as a vacant space. So which is called as an impurity defect. Understanding? So one empty space will be created when doping with the SrCl2 with the Na plus. Now you tell me, suppose you have taken the same NaCl crystal and doping with the AlCl3. Now tell me each Al ion will occupy how many Na plus ions? Each Al ion will occupy how many Na plus ions in the crystal?
3, sir.
3. But how many vacant spaces will be created?
Sir.
Hmm?
3 spaces.
Vacant spaces. If each Sr plus 2 is occupying 2 Na plus ions now, one place is occupied by Sr plus 2, right? That means remaining only one is a vacant.
Yes, sir.
Each Al plus ion can occupy 3 Na plus sites, so that one Na plus site is occupied by Al plus 3 and remaining 2 will be vacant. Understanding? Clear now? So this is called as an impurity defect. Okay. So these are the different defects in the solids. So in the starting, we studied about the point defect and the line defects. In the point defect, the defect is possible only at the particular point in the solid. The next one is the line defect, which is available along the complete row or the column. The next one is a point defect, again 3 types: stoichiometric, non-stoichiometric, and the impurity. So stoichiometric again 4 types: Schottky, Frankel, vacancy, and the interstitial site. Non-stoichiometric how many types? Metal excess and the metal deficient. And the last one is the impurity defect. Okay. So all this we covered. Any doubts in the defects in the solids? Any doubts? Any doubts in this chart or any doubts in the defects in the solid?
No, sir.
Sorry.
No, sir.
So next one is the, just wait a minute. So after this, we'll study about the electrical properties of the solid. Can you see the screen first? The next topic is the electrical properties of solid, which is explained with the help of the band theory. Okay. So electrical properties of the solid, which is explained with the help of the band theory. So before going this, when we study about the electrical properties, we have the 3 different types of materials will be there. One is about the conductors. What is the meaning of conductors? What is the meaning of conductors? Which are the substance which will allow the flow of current, right? Is called as a conductors. Which are the substance conduct the electricity? Those are called as conductors. But totally we have the conductivity range in the order of 27. Okay, first we'll start from 10 power minus 20 to 10 power 7 ohm universe, meter inverse. Okay, so flow of electricity through substance, that is called as conductors, which has the conductivity range from 10 power 4 to 10 power 7 ohm inverse. Okay, ohm inverse, meter inverse, these are the conductivity range for the conductors. The next one is the semiconductors. Okay, so this will have the conductivity less than the conductors but greater than the insulators, so which will also allow the partial flow of electricity. So it will have the conductivity range from 10 power minus 6 to 10 power 4 ohm inverse, meter inverse. Okay, and the last topic is the insulators. What is the meaning of insulators? Does not conduct the electricity, right? Does not conduct the electricity. So which will have the conductivity range from 10 power minus 10 to 10 power 10 power minus 20 to 10 power minus 10. There is a conductivity range for the insulators. So total, if you take the conductivity range, it will start from 10 power minus 20 to 10 power 7 home universe, matter universe. So insulator first, because this will not conduct the electricity at all. Next, semiconductors will come. In the last, conductors will come. So conductors are the good conductor of electricity. So it will have the conductive range of 10 power 4 to 10 power 7. Semiconductors, what is the range? What is the range for semiconductors?
Ten power minus 6 to 10 power 4 minus
10 power 4. So now we'll come back to this explanation about the conductors, semiconductors, and insulators using the band theory. So first we'll draw the conductors. Next, insulators. Or we'll go for the semiconductors. The last one is the insulators. So total we have the two bands. One is a valency band, the other one is a conduction band. Like this. So the below one is called as in valency band, which means the valency electron will be there in this band. And above one is the conduction band. So electrons always will move from valency band to the conduction band during the conduction of electricity. The next one is the semiconductors. Again, it will have the two bands, but the gap between the bands is different. And the last one is the insulators. Like this will run. Okay, if you notice the gap between the two different bands, in the case of conductors, the band gap is very, very small, right? The gap between the valency band and the conduction band is very small. So that what will happen, whatever the electrons are there in the valency band will flow easily into the conductor band. So with the help of this flow of electrons only, they will act as a good conductors. And whatever the gap is there between these two bands is called as a forbidden gap. The gap between the valency band and the conduction band is called as a forbidden gap. Okay, in the case of semiconductors, what will happen? The bottom one is a valency band and above one is a conduction band. But whatever this forbidden gap is there, which is very high in the case, which is somewhat high in the case of semiconductors when you compare to the conductors. So because of this only, whatever the electrons are there, it will not move easily from conduction band to the valency band. So due to this only, it will conduct only the partial amount of electricity. If you take this, all the electrons will move. In the case of conductors, but in the case of semiconductors, only few electrons will move from valency band to the conduction band. So due to the movement of these few electrons only, there will be the partial conduction of electricity. So this is called as an energy gap. In the case of semiconductors, the energy gap will be in the range of 1.5 to 3 electron volts. But if we take the energy gap in the case of conductors, it is almost equal to 0. Okay, now in the insulator case, this is a conduction band, this is a valency band. Now tell me whether electrons will move from valency band to conduction band. Is it possible?
No, sir.
Why? Because the distance between these two bands is very large. So electrons cannot move at all from conduction band to the valency
Valence.
band. And whatever the energy gap is there, it will be greater than 3 volts. Okay. So due to no movement of electrons from the valency band to the conduction band, these material will act as a insulators because they will not conduct the electricity at all, right? For the conduction of electricity, two important conditions are required. Either they should have the free valency electrons or they should have the free ions. So if you take the metals, there is no possibility for the ions. So only with the help of the valency electrons only they will conduct the electricity. Okay, so this gap is very high in the case of insulators only. They will not move from valency band to the conduction band. But when you compare to the conductors, the gap is very less. So the electrons will jump easily from valency band to the conduction band. Can you hear me? Hello. Hello. Fine. Any doubts in this band theory? Any doubts in these three band theories?
No, sir.
Okay. Now we don't have any chance to increase the conductivity in the case of insulators because the gap is very big. But when you take the conductors, the gap is very small, so it will conduct the electricity easily. Only we can increase the conductivity in the semiconductors by doping process. Okay. So if you add some impurities to the given semiconductor, which will cause the increase in the conductivity of the solids. So that is only called as in doping. So what is the meaning of doping? Adding an appropriate amount of the suitable impurity to increase the conductivity of the semiconductors is called as in doping. Okay, just wait a minute. I will write the definition here. To increase the conductivity of semiconductors by adding an appropriate amount of suitable impurities. So to increase the conductivity of the given semiconductors, we'll add the suitable impurities to the given semiconductors. That is only called as in doping. Do you know the elements present in the group number 13, 14, 15? Anyone in the group wise? Because if you see the periodic table, whatever the elements are there in the group number 13, 14, 15 and the 16 will contain all the three types. Metals will be there, non-metals will be there, and the metalloids will be there. Right? And germanium, silicon, these are the semiconductors. Okay. So any one of you can tell me the elements present in the group number 13 and the group number 14 and the 15? First, give me the reply whether you know or not.
Don't know, sir.
Don't know. Good. No problem. Next. What about the other two? At least can you tell me what is the valency of group number 13? Group number 13, group number 14, and the group number 15. It is very important. You have to compulsory remember the elements in the group wise. Complete S block elements and the P block elements. Compulsory how to remember in the group wise. Because when you study that their chapters in the inorganic chemistry, you have the separate S block chapter is there, P block chapter is there. Again, we'll study the different properties like atomic size, ionization enthalpy, electron negativity, electron gain enthalpy, right? So metallic character, non-metallic character, acidic nature, basic nature, all we'll study according to the group wise only, either top to bottom increase or top to bottom decrease. Okay, so that was your homework today. Study the group wise elements of S block elements. S block means what? How many groups are there in the S block? How many groups are there in the S block? First of all, how many elements are there in the periodic table? Unmute yourself and you can answer the question.
I forgot all this.
You forgot all those, okay. But at least you should know the number, right?
Mm,
Okay, you can tell me randomly, no problem. If it is wrong also, no problem. All the three.
Tomorrow I will tell, sir.
Hmm?
Tomorrow I will tell.
Tomorrow you will tell, okay. What about the remaining two? It's okay if you forgot now. We are the human beings only, right? So you'll forgot, no issue in that. But again, just go and recall those elements. That is important thing. Once you forgot now, you will keep like that, always forgetting now. You can't do anything. Whenever you are forgetting, just again open the book and again study once again, so that you can easily remember. What about Dhairya and Vishwanath? Hmm? So I'll teach you what is the group number 13, 14, 15 and all. So one small trick is there. If you want to remember the elements in the group number 13, brother Andrew got intelligent thought. Okay. So if you take brother Andrew got intelligent thought. So if you take the starting elements like B for boron, A for aluminium, G for gallium, and I for indium, T for thallium. So these are the elements are there in the group number 13. Compulsory how to remember in the order wise. So if you remember this statement alone, you can remember all the elements in the group number 13 in the order wise. Brother Andrew got intelligent thought. Next, anyone group number 14? Okay, I'll write the statement here. At least with the help of starting letters, can you tell me? What is the first one? Carbon. Next one. Can someone go to left? S for silicon, G for germanium, T for tin, and L for lead. So carbon, silicon, germanium, tin, and the lead. All these are the elements belongs to group number 14. And group number 15? What is the starting element? Nobody passed away answers back. This is a statement which you can remember easily. So nitrogen, phosphorus, arsenic, antimony, and the bismuth. So these are the group number 15 elements. Okay. So group number 13 is a boron, aluminum, gallium, indium, thallium. 14 is a carbon, silicon, germanium, tin, lead. 15 is a 14 is a carbon, silicon, germanium, tin, tin, lead. 16 is a silicon, aluminum, gallium, indium, thallium. 17 is a boron, aluminum, gallium, indium, thallium. 18 is a carbon, silicon, germanium, tin, lead. 19 is a carbon, silicon, germanium, tin, lead. and 15 is the nitrogen, phosphorus, arsenic, antimony, and the bismuth. And if you take the group number 13, the general oxidation number will be the valence will be the +3. Group number 14 +4, and the group number 15 +5. But when you're studying in the group wise, as we go down due to the inert pair effect, +2 charge will decrease. That we'll study afterwards in the separate chapter in the P block elements. So up to now you can remember as a group 13 as a +3 charge, group 14 as a +4 charge, and group number 15 as a +5 charge. Now tell me, what is this +3, +4, +5? What it indicates? What's the meaning of that? The +3 indicates the number of total valency electrons. Number of valency electrons, that is nothing but the whatever the electrons are there in the outermost shell of an atom, that is called as valency electrons. So if you take the group number 13, there are total 3 valency electrons will be there. If you take group number 14, how many valency electrons are there? Group number 14, how many valency electrons are there?
4, sir.
4. Group number 15,
Mm.
5 valency electrons are there. Good. Now if you take particularly like silicon and germanium, how many valency electrons are there? If you take this particular group, how many valence electrons are there? 4, right? Like silicon or the germanium will have the 4 valency electrons. Now, if you are doping this silicon germanium semiconductor with the 13th group elements, either you can take aluminum, gallium, okay? Or gallium if you take. If you are doping the silicon germanium with the gallium or the aluminum, what will happen? It will form the P type of semiconductors because of deficiency of valency electrons. In the case of group number 14, we have the 4 valency electrons. In the case of group number 13, we have the only 3 valency electrons. So due to deficiency of one valency electron, it will cause the P type of semiconductors. P is nothing but the positive. So increase in the conductivity of the semiconductors due to the positive charge. That is called as P type of semiconductors. Now, when you are doping the same group number 14, silicon and germanium with the phosphorus or the arsenic, what will happen? +4 is there, +5 is there. It will form the N type of semiconductors. Okay, because there will be one extra valency electron will be there in the group number 15. So this one extra valency electron will cause the conductivity range to increase. Clear? So group number 14 doping with the group number 13, what type of semiconductors will form?
Positive type of semiconductor.
P type of semiconductors. Group number 14 and 15, N type of semiconductors. Okay, now tell me which one is electron rich impurities and which one is electron deficient impurities here. Which one is electron rich impurities and which one is electron deficient impurities? Any idea? This is the electron deficiency, right? Group number 13. So this electron deficient impurities. This is electron rich impurities. Clear? Electron deficient means less number of electrons will be there than the required quantity. Electron rich means having more electrons than the required. So group number 15 is electron rich impurities, and the group number 13 is the electron deficient impurities. So with this, we'll stop this today's class. But if you have any doubts, you can ask me.